So today we're going to be looking at absorption and emission spectra. And we're going to start off with absorption. And let's say we had an atom. So an atom made of just some positive nucleus and we have like shells surrounding this atom. And we know that these shells have different energy levels. So there's obviously the ground level, then there's the first, the second, and the third, and so on and so forth. And these have some arbitrary value. So let's say this one might be 13.6 electron volts, this one is minus 8.6, minus 7.4, and minus 6.8. And let's say we have an electron orbiting this atom in its ground state. And let's say light is coming in and hitting this electron. And this light consists of all the different kinds of wavelengths. And for an electron in the ground state, it can absorb a photon of 5 electron volts of energy. And it will take a photon of exactly 5 electron volts of energy. And it can therefore get excited from the ground energy level to the first energy level. But what it could also do is it could also take the required energy to get to the second energy level, or the third energy level, and so on and so forth. So what's going to happen is you're going to get quite a variety of photon energies being absorbed by the electrons. So let's say we had the screen behind this atom here, and that screen had a detector. And it had a detector ranging from shortest wavelengths to longest wavelength. If all the light were to hit this detector, you would see a rainbow pattern. However, as it passes through this atom, some of the photons get absorbed by the electrons, and the electrons therefore get excited, the key word being excited, into higher energy levels. Therefore, you will start to see black lines in this colourful emission spectra. And these lines are known as absorption lines. And this is because, well, a specific photon with a specific energy will get absorbed. And we know that energy is equal to hc over lambda. So therefore, a specific wavelength must be absorbed. And therefore, there will be black lines at that specific wavelength, or that specific lambda value. These lines here represent the wavelengths of photons that are being absorbed by the atom such that the electrons can get excited into higher states. Now, this isn't the only way an electron can get excited from a lower energy level to a higher energy level. Another way is if you have an atom and you have a collision between the atom and a charged particle. If there is a collision, electrons can gain some of the Ke from that collision and absorb it to excite to higher energy levels. Now, one thing that you need to know about excitation is that when electrons are excited, excited states are temporary. And what that means is electrons will then look to get de-excited. So they'll always try to look to return to lower energy levels. So let's say I have a couple of electrons in the second energy level here, and they have been excited from one of the previous ways, either by absorbing a photon or through a collision of charged particles. So what's going to happen, as I said before, this state is temporary. So these electrons are always going to try to get de-excited. So one way it could do is it could just go straight from that energy level to the ground energy level. Or what it could also do is jump from the second energy level to the first, and then from the first to the ground. So here are 3 possible paths that these electrons could take. But what happens when an electron de-excites is it releases energy. And it releases energy in the form of a photon. Now, as you can see, these energy levels are discrete. They have specific values. So therefore, a photon of specific energies, or photons of specific energies, will get released. And once again, Since the energy of the photon is related to the wavelength by E is equal to hc over lambda, if a specific energy of photon is released, a specific wavelength will also be released. So if I put a screen here, and again this screen shows a range of wavelengths from shortest wavelength to longest wavelength, what I'm going to see on this blank screen is colored lines, and it may look something like that. And what this represents is an emission spectra. These are emission lines. So what you will see are colored lines at the specific wavelengths of the photons that have been released due to the de-excitation. Now, if you had an electron or electrons in this third energy level, a common multiple choice exam question could be, how many colored lines will you see in an emission spectrum? And that is governed by how many different paths this electron can take from this third energy level to the ground energy level. So let's go through that. It can take a straight path from the first one to the bottom one. It can take a path from the third energy level to the first energy level, and then from the first to the ground level. It can take it from the third energy level to the second energy level, and then straight to the ground energy level. It can go from the third to the second energy level, and then to the first, and then to the third. So the number of lines are governed by the number of different energies of photons released. We can see here that these two de-excitations will give the same line on the screen, and so do these two. And then there are another 1, 2, 3, 4 different paths that this photon can take. Therefore, there will be 6 emission lines on the emission spectrum. Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.